Hello class, today I'm going to talk about one-dimensional Schrodinger equations. The aim for today is students should be able to derive Schrodinger equations and importantly to analyze the solutions. Now when we talk about one-dimensional system, so the idea physically means that your particle move only in single or one direction. Okay, now for example, look at this tube. Okay, so we have an electron E traveling one direction through evacuated tube given by these potentials. Okay, now let's try to start with your Schrodinger equation, which is equation 1. Now look at this. So you have your reduced Planck constant. Here this comes from your kinetic energy, and then this is your potential energy. Alright, let me use the red color. And then you have the potentials given to you, and this is your eigenvalue of your spectrum of energy. It gives you energy. So recall you have this. So your H is kinetic energy plus potential energy. Now I drop the sign of this is functions of x, so just psi. Okay, all of my notations will be psi. Now if we rearrange, look at this. Let's say if you start with your v naught or vx just 0. So you rearrange given your E side to your left, and then you only need 1 multiplied with the second order differential. So you have this, and you can have plus sign. So you have 2me over h bar square. Then you can come up with a single constant. You can parameterize your Schrodinger equation with a single constant k. It's either k, okay, you have two options to write your single constant k, or you have k square. Alright, why there is some easier choice? Because let's say if you want to find the roots, okay, to find the solutions of your psi, then if your second order derivative is r square and then this is your k square, so if you try to find r, they're just plus minus ikx. But let's say if you stick with the first options, r square equals to k, then your r is equals to plus minus I square root k. So your solutions either this one, number 1, or you can find another solutions since you have a complex root minus I square root x plus a2I square root kx. Okay, so you have that. So it's either. So now if your v is not equals to 0, so you have v naught, so what you do, you just include v naught inside your second terms, and you are producing the same thing, either the first options here or the second options like this. Okay, so your k will be either this, or if your k square is equivalent to that, then you see you have a square root of everything with h bar. Okay, so in this case, if you're finding the roots, so I go back to the sense, so now your k here, so maybe I put, if your k1 having v, so you have k1, 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 and k1. Alright, so again your solutions either this or this. Alright, similarly you can rewrite your solutions in terms of cosine using the Euler form. This you can try out later on. Now let's go back to your potential step. So we come back to this region, okay, and usually we have region 1 and region 2. Okay, let's go back to this. All right. So in this case, so I rewrite again what will happen. You always consider case 1 and case 2. So your case 1 is the energy of the particles much larger than your potential, and case 2 is the energy of your particles less than the potential given. Okay. So every time, so we start with case 1. So case 1 always have 2 regions. So this one is looking at this part. Okay. So in this case, maybe I should remove this. We don't have this. Okay, don't have this. All right, good. So in this case, look at what you have here. When you have a traveling wave, incident wave, your V naught is equals to 0, so you don't have V naught here. Then you are producing, so I'm choosing K squared. Because you are dealing with region 1, then I have psi 1. So I'm producing complex roots. So you have I kx and B1e I kx. This one. Now if you look at the second region, okay, so second region I have K2, so K2 here respect to second region. So in this case, I have my V naught. But my V naught here, E minus V naught always larger than 0. Okay? So in this case, you also produce the same as the first region, where you have a complex root. And this is what happened for the second region. First region. Alright? But let's say you want to change this. Okay? You want to make some change respect to algebra. Okay, I want to make a minus sign over here so that I can change in terms of the solution of your differential equation. So I have a minus sign, so I can rearrange V naught minus E. So I came back at this. This is your roots. These two are equal. But then you notice that in this case, V naught minus E always less than 0. Okay? Because your E here is large, very large. So they give back the negative of your K1 squared, and then it's a complex root. Alright. So next, to solve B, A2 and B2, this is when you want to talk about reflection transmission coefficient. There is some physical significance to this. Okay, so your A1 represents the rightward moving, and your B1 leftward moving of the particle. All right, and we're going to look at this afterwards. Okay, but you hold on to that first. Let's try to look at case number 2, where your E is much less than your potential. This is your particle. Okay. So again, you have region 1. So this is associated K1, the single constant. This is associated K2. All right. So in this case, you look at the first region. This part very similar to the case of E larger than V naught. So we are going to concentrate on region 2, where region 2, your V naught is much larger than E, or your E is less than V naught. Okay? So in this case, you have E minus V naught is always negative. Okay, so it will be different from producing a complex roots. You are only deal with real roots. So the solutions to this is like that. Okay, so you don't have I at this point. So your solutions for the second region is this. Okay, and then you can apply the continuity equation to solve equation, but that will be later. So at this point, make sure you can identify the solution to Schrodinger equations over some region. Okay. Later on, please submit. There's one examples where I will put up next. Okay. The highlight would be, look at this one. So plus sign, it will be an incident K1. So if it's bounced back, it means that you have the reflection, and minus k Ix. So this is incident, and if you have something that is going through, okay, then you have some transmitted. Okay, please have a look at your notes again. All right, thank you.